In this video, we'll talk about how ordered lattices can be further divided into unit cells, which are basically repeating units that contain some characterization of the ordered lattice. Our learning goals in this case will be showing how ordered solids can be depicted as a 3D array of repeated unit cells, and showing how the different interstitial sites in a lattice can have different sizes and how we can specify what those sizes are. Now, I want to mention that there are some even better videos depicting unit cells that are in the lessons, so you should watch the ones that are created by Manuel Moreira Batista. They're really great computer animations that will show you how the unit cells fit together to form an ordered lattice. So, what are unit cells? Essentially, a unit cell is the smallest repeating unit that you can find in an ordered lattice. The unit cell should have the same elemental composition as the lattice itself, and it should reflect the geometry of the lattice, whether it is a body-centered cubic or a face-centered cubic or a hexagonal closest packed type of structure. So what you can do is, if you get the unit cell, you basically have a small condensed abbreviation of what is going to be true throughout the entire ordered lattice. So let's see what they look like. Let's build a unit cell. I'm going to start by building a face-centered cubic unit cell. So it has atoms at each corner of the unit cell and in the middle of each face, thus face-centered. Now we'll create this whole unit cell. Now I need to add 4 more atoms at the centers of the faces. So this is basically the unit cell for a face-centered cubic lattice. It's a cubic unit cell, thus the cubic, and it's got atoms on the center of each face, thus the face-centered. So now if we were going to construct an entire array out of this, we would need to add many more unit cells that would connect to this one. So it might look something like this. I've connected 5 of these unit cells together. You can imagine connecting hundreds and thousands and millions of these together to create a whole ordered array. I want you to note that the facial atoms are shared between 2 different unit cells. So in effect, each unit cell only gets half of that atom. Similarly, the corner atoms are shared by 8 different unit cells. So in effect, the portion of the atom that is in each unit cell is 1/8 of the atom. This means that the total number of atoms in each unit cell is 8 times 1/8 plus 6 faces times 1/2 each. So it's a total of 4 atoms. So each unit cell in this array contains 4 atoms. So the total number of unit cells will be the total number of atoms divided by 4. We can also do this for a body-centered cubic unit cell. And this unit cell looks as follows. We're going to have atoms at each of the vertices. We'll put in another face here, atoms at each of the vertices, connect them up to make the cube, and then we'll have 1 atom in the center. So this is the body-centered cubic unit cell, and again, if we create the extended lattice, we'll be putting many of these together. The total atoms now are 8 times 1/8 for each of the atoms on a vertex, plus the 1 in the middle. So each of these unit cells has a total of 2 atoms. Now, we're also going to be interested in the coordination numbers of the different atoms in these cells. That coordination number is the number of nearest neighbor atoms, that is, the ones that touch it, if you will. So for closest packing structures, we have seen that the hexagonal ABAB and the cubic ABC represent the most efficient closest packing. Does that mean they have the same coordination numbers? Well, as we build them up, we put the second layer on the holes above the first. There are 3 now. If this is our reference atom, there are 3 touching that reference atom. Okay, there will be 6 more that are in the same layer as the reference atom, so that will add 6 more to it. And then on the top layer, we'll add 3 more. And notice that the 3 on the top layer are oriented differently. The hexagonal, they're oriented exactly as they were in the first layer. In the cubic ABC layer, they're not oriented the same as in the first layer, so they don't overlap them. So, but in each of these cases, we have 3 plus 6 plus 3, or a total of 12 nearest neighbors. So that means that the coordination number for these closest packed hexagonal and cubic face-centered cubic are both 12. If we look at a body-centered cubic, if we start with 4 atoms on the lower layer, our reference atom will be the one that goes on top of that, so it has now 4 nearest neighbors. And now when we put in the next layer, there will be 4 more added, so we'll have a total of 8 nearest neighbors. So it has a coordination number of 8. So here again, you can see that the hexagonal and face-centered cubic closest packed structures are more efficient because they have 12 nearest neighbors, whereas the body-centered cubic has only 8. Now we can get these coordination numbers also from looking at the number of nearest neighbors in the unit cell. But the way we're going to do this is by putting 2 of these unit cells together and using a facial atom as our reference point. All right, now to start with, we'll count the ones that are in the same face as that atom. There's 4 of them that are located the same distance away. But there are also 4 atoms that are located that same distance away, colored yellow here, that are in the faces of the adjacent faces on these cubes. So that adds 4 more. Finally, we'll add 4 more, these green atoms that are in the middle of the vertical faces. So we have a total of 12 now that we're able to draw for the face-centered cubic lattice. And the body-centered cubic lattice, we will just use the middle atom as our reference point, and we can see immediately that it is closest to 8 different atoms. So it has the same coordination number that we found before. So you can see that these coordination numbers are reflected not only in our packing arrangements, but also when we draw these unit cells for each of the different schemes. Let's take a look at interstitial sites. An interstitial site is the gap or the void between the spheres in a closest packed lattice. A tetrahedral site is one that's formed by 4 spheres, and an octahedral site is formed by 6. Okay, we've talked about this before when we were building up these close packed lattices, but let's look at them again now. So here is the beginnings of a tetrahedral site, to which we're going to add an atom on top. When we connect all of the dots here, we'll see that these things form a tetrahedron. And so the space that's in the middle of these 4 atoms is going to be a tetrahedral interstitial site. This is what it looks like when we draw it actually in the curvilinear spherical dimensions of those regions. Now let's do the same for the octahedral site. So again, we'll start with 3 on the bottom, and now we're going to stack 3 on the top. This is the way we formed an octahedral site in the hexagonal arrays. Okay, now we're going to connect things up this way so that we can take this set of 6 atoms and rotate them and better visualize what that octahedral site looks like. It's much easier to see now that these 6 atoms form an octahedron, and the interstitial site now is going to be an octahedral interstitial site, and this is what it might look like when we take into account the 3-dimensional geometry of the spheres in that site. Now the size of interstitial sites is going to be very important for us because when it comes to making ionic compounds, some of those ions are going to fit into the interstitial sites between the larger of the 2 kind of ions. So this is going to be very important. It's also important when we look at impurities that are put into metal lattices or various alloys that involve interstitial substitutions of a different substance in the metal crystal lattice. So the size of the interstitial site is going to depend upon what atoms can fit in it. I'm going to use a little r to represent the radius of the sphere that would fit into a small interstitial site, and big R as the radius of a closest packed sphere. Now we can find the relationship between these two just by using simple geometry, although maybe it's not so simple geometry. It's probably a little bit more detailed than what you would have learned in school. Nevertheless, it's not a complicated operation. It's just a matter of using geometry. We find that a tetrahedral site, the size of the interstitial tetrahedral site is related to the size of the spheres that form it by a ratio of 0.225. For octahedral sites, it's a little bit larger. It's 0.414. So this tells us that tetrahedral sites tend to be smaller, so it's going to take a smaller atom or smaller ion to fit into those sites, whereas octahedral sites can accommodate a larger object placed inside there. This is just a demonstration of how you can compute this geometrically. I'm not going to go through this, but I've given it to you here, so if you want to pause your video and work through it yourself, you can. This tells you how to get the size of an octahedral site.